Welcome back. It's been a long time since I've put up a video, but I want to thank the people that have subscribed, and I also want to thank the people that have commented. There have been a few people that asked me some questions. That's great. But I want to start with just a little bit of discussion on how to do the basic conceptual design to, as best as you can, arrive at something that'll work in the future without much trouble. Now, this is a very complicated topic, and I'm not going to cover it all in one video. That would be impossible. But I'm going to give a shot of just some rough ideas at a high level of what I've learned over the years. So, the first thing when you think about conceptual design is trying to determine what is the major thing you're trying to accomplish. This needs to be a very specific, very well-defined thing. A good example of this would be, I want to design an airplane and I want it to carry two people. I want to fly 500 miles or have a 500-mile range, maybe with contingency. I can specify how much. I want to get a 500-mile range. And I want it to cruise at 300 miles an hour. Okay, that right there has defined, I know I'm making an airplane for two people. It has a range and it has a speed that I want to achieve. Right there for an airplane, that narrows everything down pretty well. Other industries, it may be a little bit different, but you want a specific thing that you are trying to accomplish written down somewhere. You can't work with vague goals. I'll just say that often in industry, when I was working, doesn't matter what industry actually, I've worked in several, getting these specific things written down by someone is a challenge. A lot of people want to be very squishy and want to try to, or they want to not only be vague or non-committal on what they want to accomplish, they also want everything out of the design. They want to do this and that and that and that too. And this could be completely conflicting things. But your job as a designer is to the best of your ability get people to sit down and agree on something that they believe in, that you can write down, and it needs to be concrete. Not a picture of something yet, no pictures, just what is the idea of the thing that you're trying to accomplish. Write it down on a piece of paper. That needs to be what you work towards. And that can change, but you have to start somewhere. Okay, so you have an idea of what you're trying to accomplish. As I mentioned, one of these ideas is an airplane. Now, if I was brand new, never designed an airplane before, I've actually worked a little bit in the airplane industry. I know a few places to look, but I may even own some books on airplane design. But once you have these ideas written down somewhere, then you start researching what has been done before. You go and you look and find out what other airplane designers have done, the choices they have made, just at the rough level, what things look like, what to expect, what you don't see. That's another hard question to ask yourself is, what do I not see being done? And this could just, you might want to write this down so that you can then keep asking that question. Maybe it'll come up in manufacturing later. Maybe it'll come up in something no one's thought about. These things happen, but you want to do research and understand what has been done before. Another thing, a trap that I see some people falling into is they will see what has been done before, and they'll see something that they don't really understand. A wing shape that looks like this, well, why not like this? Or they'll focus on what they're experienced with, but they'll ignore what they're inexperienced with. For example, guys that are really good at working with fluid mechanics will often forget something about structure, or structural guys will forget something about fluid mechanics. Both, unfortunately, will probably forget or not really understand or have experience with manufacturing, sadly. So it's important to when you're looking at at something that has been done before, to try to understand not only all the different physics part of it or parts of the design, but also um, how they actually manufactured things. It's one thing to look at a Ferrari on a road and say, "Man, that thing is beautiful. Look at that, all that beautiful shape, that gorgeous shape, and the engine and everything like that." But what you don't see is a big factory where you had to pour the metal for the engine. You had to put together all the composite body materials, have all the workers put it together. You don't see that, but that needs to be part of your thinking for the conceptual design. Is not only do you want to see the final part and what it looks like, that's great, but you want to have an idea of how big this manufacturing facility is to make it. For something really simple, like a pair of scissors. Oh, I wish I. Let me go grab that. For something really simple, like a pair of scissors, you may think, oh, well, it's just a pair of scissors. It can't be that hard. But look at it. I've got two pieces of metal sharpened. I've got a joint here with another piece of metal with some plastic that lets it slide. And I've got these plastic pieces, which it looks like these are two different grades of plastic. They're definitely two different colors. I don't know how I make this right now. I don't know how we attach these arms here. So this is, even though this object is just a pair of scissors, seems very trivial. There's actually a lot of thought that went behind this, and the facility to make these, what I need to get done, including sharpening, getting the metal, even etching the names on here. There's some writing on here. Somebody had to think that out, and I don't consider something a solid concept until not only it considers the final object, but it also considers the basics of how you even the factory that it takes to make something like this. Maybe you're doing a one-off prototype. That's fine. You may be able to have some leeway there, but if you're making or designing a mass-produced concept of something, you really need to bake these into the initial stages. So you've done some research. You have your airplane or whatever you want to design. You know what it needs to do. So you've done some research on similar designs before. Now is the time, after you've done that research, is to do the basic math. For the primary things, for an airplane, I would say, well, I know its range. I know how much it needs, how many people it needs to carry. I know how fast it's going. How much fuel does it need to get to that range? Okay. Then how much, what kind of engine will it take to fly that speed? Okay. Well, I know these things. Now I know the engine's going to eat this much fuel. That means it needs to be this efficient. Oh, now my weight would need to be higher. And I just do the really basic rudimentary math on these things to figure that out. And I might say, well, the structure weighs this much and just throw a number out there and just start there with a basic idea of what I've got. That's the math. That's the primary part of it. That's the part that's fundamental to its mission, is just that part. Now, once I have that first part done, then I would either myself or through a consultant or an expert contractor, someone, depends on how big this project is, I would then try to do the basic math of the secondary things. And secondary things, I would mean something like the basic structural layout. How big do the members need to be to get the stiffness that I want? What are the controls of the airplanes going to look like? What does it need to have to be stable? Just the basic math, not a whole bunch of details, but just something that I can rely on that'll likely work. Unfortunately, a lot of design books don't cover some aspects that well. I know I've done some work in heat exchangers. They don't talk that much on good structural side of thing, on a good structural design of heat exchangers. That's unfortunate, but that's just how it is. You have to be really careful about these things. But you want to cover the basic secondary aspects. like structures, like for an airplane, controls, things like that that aren't so intuitively obvious. The primary things being related to the mission. Secondary things are secondary not because they're not important, but because they may restrict those primary things. The more structure I have on an airplane, the heavier it is, the the more fuel I'm going to burn carrying around that structure, or the slower it'll go, less performant it is. So you have to be careful of these things. So you want to have some basic math there, but you just want to have enough math there to say, yeah, I think this will work. I have the spreadsheets to show, yeah, the idea seems valuable. It's not too out too off the pasture here. So you're just feeling things out and just trying to find the overall important laws of this idea. What governs? What are the things that may not be intuitively obvious at first? Just seeing the airplane, you may not think about the control systems and how the size of the control surface impacts the design. You may not think about that. You just see the airplane like, and you think, ooh, that looks pretty. Ooh, that looks fast. Oh, it can carry this much weight and fly this far. Oh, that's great. You want to go a little bit deeper than that, but not down into details. You don't want to know down to the last number of how many bolts, nuts, and rivets there are in this airplane. You don't want to go down to that stage. You're just trying to feel out the physics of the idea. Basically, you want to squint your eyes at a spreadsheet and look at it, kind of a rough shape of things, and say, yeah, that'll work. Now, you want to start doing the iterative part here. I'm still considering this a pre-conceptual stage. You have some math, you have the fundamental requirements, and you want to look at a few different configurations. Yeah, I have this airplane, it wants to do these two things, but where do I put the engine? Do I want it front mounted? Do I want it rear mounted? Do I want to use a jet engine? Do I want to use a propeller? Do I want to have retractable landing gear? These are all good ideas, and they've all been done before, but I want to kind of feel out the impact of these different things. Some of this can be informed with research. And you want to create a big array of ideas and just come up with what seems reasonable with you at first, and how much is informed by the calculations that you have done. So to the first level, you want the impact of these various different things on your performance of this airplane or what it is you're designing. And after you've done that, then you step into the next stage of the iteration, which is figuring out how you would actually build the thing. And by that I mean, I'm designing an airplane. I could make it all out of one piece of composite, or I could make it multiple parts, including the wings would get bolted onto the airplane somehow. How does that look like? What would the size of the building look like that it would take to make this? Do I have that available? This engine I selected, or one of the engine I selected, what's the lead time on that? How available are these things? Are these things? Will it take a new engine entirely for this configuration? Is there even someone who's making a cooling system for this engine that can reach it if I mount it on the back of the airplane? These are kind of things you should be asking, not doing so much math that you go and bury yourself into a book for a month that you forget the meaning of life and everything else, but enough that you understand the various impacts of your decisions, including the size of the building or the different processes that go into making this thing. By this, you just have a huge array of things, and depending on what you're working on, it can be very difficult to narrow things down. And this is why it's helpful to have a good experienced group that you're working with, because they help you keep you out of too many rabbit holes and going down too many blind alleys. But you want to then research. You have all these ideas, and in this way, they could be novel ways of building things. We want to do a little bit more research and investigate what has been done before. Some things, especially when it comes to manufacturing, are very difficult to find. You go out there and you see a shiny new airplane, and some things you can figure out how to make, but sometimes they do something that's very clever that they will not tell you how they build it. So you may have to do some research or some kind of studying on your own to figure out how things have even been built in the past. Maybe calling some suppliers if they'll even tell you. This information can be very hard to come by, and so that's why it is very helpful to be informed by experience. That's just a sad fact of life. You won't know how to do everything. You can do some research, but sometimes you just have to try some things. A good example of why you want to do research is I've worked in the past on airplanes, like I said. Welding aluminum is not something that you normally see in a lot of airplanes, and that's because airplanes are usually these big, very large parts made out of very thin metal. And welding aluminum, at least normal welding when you have molten metal, not when you do stirred friction welding, like some rockets use. But normal welding, it requires melting of the metal, and the heat from this molten metal spreads outside the joint to the adjacent metal. This weakens aluminum pretty substantially. And then to return the strength back, you have to then do a proper heat treatment of the aluminum. And this requires an enormous oven. So you would need to then do this weld, then put this huge piece into an oven, properly bake it. And when you bake it in the oven, it often goes from this nice straight piece to this curved up shape that would make a really crappy wing. That is one reason. Another reason is if you then say to the FAA, the Federal Aviation Administration, or even EASA, the European Aerospace Administration, and say, hey, I made an aluminum airplane wing that's welded together, they would say, really? Show me that it's going to last for this many years and it's not going to have all these various problems I'm not going to go into. It doesn't. It just depends on the industry. If you have a regulatory body, you can use that for guidance. For airplanes, that would of course be the FAA. For pressure vessels and things, that would be the pressure vessel code, unless for some reason it's not required to meet that code. That happens, but you want to do some research so that you're not too far out there. And one of the reasons I bring up the welded airplane part is I was working on something that someone had the idea to make a welded airplane part, and it was just a bad idea, and it wasn't informed by good research, and it ended up with the company spending millions of dollars on it, and that was it. It was just a waste of money. The point is, at this stage, you have your concept, you have some basic spreadsheets, you have an idea of how you're going to build it. And then you can narrow down your design, because likely that these ways of building things, this airplane, for instance, will now affect other things. Like if I build the wings this one way, it'll increase the weight a certain amount. If I do it this other way, it won't. Or maybe one way of building this thing would be so big and require such a large factory that it is just not something you can do right now. It's too expensive for whatever reason. Hopefully it gets narrowed down into something design space that's still there, meaning you still have a possible solution, but it's not so many concepts that you just can't decide anything. If you're in that situation, you might not be in a necessarily a high performance industry, because things like cars, airplanes, boats, even buildings, pressure vessels, all those, you start hitting manufacturing limitations or enormous costs at some point. On some other industries, it would be driven by cost. And even something as simple as these scissors, I'm telling you, a lot of decisions came into making these things that you don't even think about when you look at them. But the point is, you should be more intelligent than to just look at the scissors and say, oh, that's easy. You should be able to have, okay, for scissors that are made this way, I have to do this. If I were to make these all out of metal, it wouldn't be so hard because I wouldn't have to join the plastic to this metal. I could do a different rivet design here. I'd have to figure out sharpening, but it would get rid of these other materials and potentially make the manufacturing size a lot easier. Would it be as appealing to the customer? That's another question. Maybe you can't make all metal scissors because the marketing guys are telling you, no, we need more comfortable scissors that are not all metal. So we need something that's, softer to the touch. And that's perfectly acceptable. That's an acceptable driver for design. But the point is for you to understand those things at the high level at this stage. So once you have these things in mind, and I see them already over 20 minutes, that is when you have a pretty solid concept. And only then can you start really throwing money at it in man hours to get something done. And I've seen this rush before, where people make decisions early. They did not consider things like all the manufacturing required to make the design work. They don't consider branches of physics entirely, and they just march down and they lock this concept and assume a bunch of things without ever looking at how it's affected. And unfortunately, that's the reality of some big companies is they do this. And I'm not even talking about one industry in particular. I've seen this happen everywhere. So it's just something to be aware of and to be wary of making decisions too early without doing these informed stages of research. So that's all I've got to say for now, and I hope you found this interesting and helpful, and I'll talk to you later.